Hello, it's Keith here, and this is lesson 24 of the platform-specific series of my Z80 programming tutorials. Over the last few weeks we've been looking at various systems and how to make sounds on those systems, but now it's time to move on. So we're going to go on to looking at how to access the RAM, the ROM, and various other resources that some of our computers may have. So this week we're going to be starting with the Amstrad CPC, and on the Amstrad CPC we will be looking at how to access the extra banks of memory, because whilst most systems on the Amstrad CPC start with 64K or 128K, some systems have 256 or even up to 576 kilobytes. And because of very kind hardware producers within the community, the vast majority of real Amstrad enthusiasts do now have 512 kilobytes of memory or more. So if you really want to go crazy, you can. Now beyond that, we'll be looking at the CPC Plus functions, how to turn them on and how to detect whether they exist or not. And we'll also be looking at how to use the cartridge memory on the CPC Plus if you're creating a ROM cartridge. The end game of today's lesson is we're going to create a function that allows us to run this function on our Amstrad CPC, and it will detect how much memory is present, either 64K, 128K or 256, and it will also detect if the machine is a CPC Plus or not. This allows us to do what Chibi did, which is load the game up, and then the game will reconfigure itself depending on whether it finds it's running on a 64K system or a 128K system, or whether it's got the CPC Plus functions or not. So we can have one game that really takes advantage of whatever system it is running on. Okay, so today's lesson is going to involve quite a lot of theory and relatively little code, but it's very important stuff we're going to be looking at. And first I think we want to discuss the gate array. Now the gate array is something we looked at before when we were doing color palettes, because we use it to select the color we want to change, and then we then give it the new color that we want that palette entry to have. That's what we used it for before, but now we're going to use it for some of its other functions, because the function it does is actually decided by the top 2 bits of the byte that we send. Because as with everything on the Amstrad CPC, the port commands use B and C combined for a 16-bit address. So the gate array is at the port 7F, and then the remaining 2 bytes will be defined by one of these. So depending on the top 2 bits defines the command we're using. The most important one we're going to be looking at today is the RAM banking option. And you can see here we have 8 possible bank switching options and a total of 8 possible banks. Okay. Apart from that though, we are going to briefly look at the ROM options as well, because when it comes to using the CPC Plus cartridges, they actually emulate the internal ROM of the Amstrad CPC, so we use them in a very similar way. Now on the Amstrad CPC Plus, the basic motherboard doesn't actually have any ROM, so if you try and turn on a CPC Plus without a cartridge installed, nothing will happen. The ROM, that is the firmware and the disk ROM, are actually built into the cartridge, and so a custom cartridge can have those in if we want, and that's how some of the conversion routines work that convert disk images to cartridges. But we don't need to have any firmware ROM in there at all. We can have entirely our own game ROM. So how does memory extensions on the Amstrad CPC work? Well, they're relatively straightforward. As with all Z80 8-bit machines, you can only access 64 kilobytes of memory, and so as is common with these systems, what we can do is we can switch in different 16 kilobyte banks of memory. Our basic 64K system will have all of its memory accessible all the time, but when we get to the 128K system, we effectively have 4 extra 16 kilobyte banks, which I've numbered 4, 5, 6 and 7 here, that we can page in, and we're given a total of 8 different options for paging those in. So if you look at this table here from C7 to C0, these would be available on a 128K system. However, on a 64K system, you would only have this option here. When you get to a 192K system, you would have an extra 8 banking options here from C8 to CF. Now, what do these options do? Well, the most common ones that I would recommend you look at are numbers C4, C5, C6 and C7. These are very simple. All they do is they page one of the extra 4 banks of memory into the 4000 to 8000 memory address range. And this is what I do in Chibi. Some of these banks will contain extra sprites, some of them contain loading screens, one of them even contains the font and the music, things like that. So that's the way you can use the banking, but there are some very special banking options for 128K systems, and these are C1, C2 and C3. Now C2 effectively swaps all of the memory out in one go, so instead of the basic 0 to 3 banks, our Z80 will now see banks 4, 5, 6 and 7. The problem with this is it will actually affect the running code. If your game or your program is running at 8000 and you switch to this mode, the next line of code will have vanished. So you would actually have to switch that bank in here, prepare it with the code so it could continue correctly, then page this in so that the program counter will actually see valid code next. So that's a very clever, powerful function, but if you're a bit uneasy on it, I'd suggest you just steer clear of it. And the other one that's a bit tricky is C1 and C3 here. You'll see in these ones, RAM Bank 7 is at the top, and RAM Banks 1 and 3 are swapped at area 4000. Now these are often used to do a page flipping function. The original Chibi Akumas on the 128K systems did this. You can basically write to the area 4000 and you can tell the CPC hardware to switch between RAM Bank 1 and RAM Bank 3 as the screen, and then you can use RAM Bank 7 as a little bit of extra memory. The problem with this is it can only be done on a 128K system. The 64K systems cannot do this, so unless you're not going to support 64K systems, I'd strongly advise you don't use this for that function, because you'll just be programming your screen functions in a way that won't work on your 64K systems. That said, they are quite useful for CPC Plus functions, and we'll see why in just a moment. So that's how our 128K system will work. But when it comes to our 192K system, we gain an extra 8 banks. C8, configuration mode C8, will do exactly the same here as C0, so we get no extra banks. And then CA will do exactly the same as C2 did, paging in all 4 of the extra banks of the 192K system into the addressable memory. CC to CF will do exactly the same as C4 to C7 did, paging in the 192K's extra banks into the 4000 range. The tricky one comes with C9 and CB. It may be the case that they also work the same way as C1 and C3 did. However, I'm told that it quite possibly won't work. Because there are no 256 or 192K official Amstrad CPCs, it all came down to the hardware the manufacturer was using, whether these would work or not. I'm told in some cases they don't work. So while you can rely on paging modes C1 and C3 existing, you cannot rely on that for these, so I would strongly advise you not using these. And I believe this one's okay, but these are certainly okay. So as I've said already, I would try and program around the assumption that you are going to be able to use RAM Banks 4, 5, 6 and 7, 8, 9, 10 and 11 if you're using 192K. In the 4000 range, you can rely on these on a 128K system, but apart from that, you're probably best steering clear of the other options. Now, if you've got even more than 192K, it's very easy. It just continues in the exact same way up to FF. So all we do in all cases is we send a number from C0 to FF to the port 7F. So we would set BC to 7F CO or 7F FF, and we just page in the memory, and the hardware does it for us, and the memory's just there. It's very straightforward. So that's the theory of our memory, and we will be coming to all of this, of course, later in practical code. So what about the CPC Plus? Well, as I've mentioned before when we were looking at palettes, turning on the CPC Plus involves sending a very random set of commands to the CRTC. Why are they very random? Well, it was intentionally obscure so people wouldn't figure it out and be able to use the CPC Plus functions if they weren't buying the license for the cartridges. But anyway, we can all use it now. Once we've sent this set of commands, the CPC Plus ASIC is turned on, and then all we need to do is page in and out its memory, and these are very straightforward commands. So we just send these to the gate array, and that will turn on or turn off the CPC Plus registers. What are the CPC Plus registers? What would you believe? They're another bank of memory, and once again they appear at the 4000 range. So we can turn on our ASIC memory at the 4000 range, and this is why I said you may want to reserve that RAM Bank 7 if you're using the CPC Plus, because you won't be able to use any of these banks if you're looking to copy sprites from your extra memory into your ASIC, because of course it will be covered up. So RAM Bank 7 is very handy for this. Another thing to bear in mind, and again this comes down to the upgrades, I had a big problem with the Chibi Akumas game. If you're going to use the CPC Plus ASIC, you should really turn off extended banks in this range, because while on the official CPC 6128 Plus, the ASIC will overlap this RAM, so you'll be writing to the ASIC. On some systems that use unofficial upgrades, that won't work, and you will actually be writing to the proper RAM. So turn off anything except C1 and C3 when writing to the CPC Plus ASIC RAM. If you want to see a little bit about the ASIC RAM, please take a look at the palettes tutorial I did before. We will be doing sprites later though, and so we'll be covering it again later. Now, we'll just briefly cover how the cartridges work on the Amstrad CPC Plus. I'm not going to teach you how to make your own cartridge. There are some conversion tools to do it, but really they're just a giant binary file anyway. Now, when it comes to the CPC Plus cartridge, a CPC Plus cartridge contains up to 32 banks of 16 kilobytes, numbered 0 to 31. Now, the first 8 of these are special. They can be paged into the low memory area and they emulate the Amstrad CPC Plus's firmware. However, there is more options for the remaining, and we can actually page in any of the full 32 banks into the top area of our memory. And it's very straightforward to do this. All we do is we consider the number of the page of 16 kilobyte ROM we want. We then add 128 to it, and we out that to port DF. This will select the bank. Then we need to page in the ROM, and we need to page in the high ROM with the bit here. And that's why I said we were going to be covering the gate array. So we need to page in bit using bit 3 here, turning this to 1. That will page in the high ROM into this area, and that will gain us access to all 32 of those 16 kilobyte ROM banks. And as an added bonus, while C000 is our screen memory address area, while reading from that area will read from the ROM, if we write to that area, it will actually go kind of through the ROM and straight to the screen. So if we were copying sprites from the ROM to the screen, we don't need to turn the ROM off, we can just write straight through, which is a real bonus if you're going to do that kind of thing. As I say, CPC Plus cartridges are really outside of the scope of these tutorials because it's quite tricky creating them, and if you're creating a CPC Plus cartridge, you're immediately cancelling out the potential of most of the CPC community playing a game, so it's not really something I'm looking at, but I wanted to cover it at this point. So that's the theory of the hardware we're going to be looking at today. Well, how are we actually going to detect it? Well, the procedure we're going to be using in all cases is very similar. The theory goes like this. What we do is we write a known value into the area around the 4000 area into the 64K of memory. We then page in the extra memory bank that we want to have, either one of the 128, 192 or the ASIC RAM. We then alter the byte at the position we just wrote to. We then page out that extra memory and we check what the byte contains. On a system with that upgrade, the byte will contain the value we originally wrote. On a system that doesn't have that upgrade, the change we did will not have applied to the extra memory because it doesn't exist, and it will have overwritten the original value. It's a very crude way of doing things, but I'm told it's really the easiest and most practical way of detecting extra memory and detecting the CPC Plus ASIC. So that's what we're going to do, and it seems to work fine with Chibi Akumas. Now, one thing we do need to bear in mind, on a 64K system, if we try and turn on the 128K RAM, nothing will happen. So we will end up writing to our original memory, which is what we expect. On a 128K system, when we page in that 128K of RAM, of course we will write to the extra bank, not to the original one. However, if we try and switch in a 256K bank, the 128K system may respond by turning on the equivalent 128 bank. So for example, let's pretend we tried to turn on bank CC. Well, the 128K system might actually turn on bank C4. So if we were writing to bank 1 here and then trying to page in the non-existent bank 8, we would actually page in bank 4, and it might look like to our system that it had successfully paged it in, but it hadn't paged in a 192K bank, it had only paged in a 128K bank. So when we want to detect a 256K system, what we're going to do is we're going to, rather than writing to the basic 64K, we're going to write to the 128K equivalent bank and then page in our 256K bank and write to that, page back to the 128K bank, see if the write has changed anything. If it hasn't, we know that 256K bank exists, and then we'll just switch back to 64K and return. Fortunately, of course, we don't have any such problem with the Plus machines, so it's very straightforward on those. And just one thing to make very clear, sending these commands to a regular non-Plus Amstrad CPC have no negative effect at all. Okay, so that's the theory. So let's have a look at our code then. So this isn't my bank swapper test code. It doesn't do very much at all really. So all we're going to do is we're going to run a command called get hardware version, and this will return a pair of values that we'll have a look at in just a moment. And then what we're going to do is we defined this base bank command, and what we're going to do is we're going to write some data into the extra memory banks here, just the bank number, which will be C0 onwards, and then we're going to dump bank 0, bank 1 and bank 2 to screen, and we're using this set current command which will page in that bank, and we'll have a look at those definitions in a moment. And then we're using the monitor mem dump to show a line or two of those banks. Finally, we're going to page in bank 5 of the cartridge memory, and we'll have a look at see if that works. So now it's time to have a look at how we're actually going to do our paging in. So here's our CPC Plus initialization commands. We just send all of these out to the system, and this will turn on the CPC Plus if it exists. It won't do anything if it does not. Then we've got our page in and page out options here, again for the CPC Plus, and again they won't cause any problems if we try and use them. So we're defining bank base on the Amstrad CPC as the pageable memory area, and then we're defining bank 0 as the basic 64K, bank 1, bank 2, bank 3, and so on to bank 8. And these are going to essentially be the extra banks of a 128K system, and these are going to be the extra banks of a 192K system. And these will all bank into area 4000. So this is making a very convenient way of us working with the extra memory on the Amstrad CPC in a way that we can actually do the same on other systems in the future. So let's take a look at Bankswitch set current. So what does it do? Well, it's very straightforward. All it does is it takes the accumulator and it uses the value in the accumulator, which will be one of these, to set the current bank configuration. And of course, those bank configurations will match something on here. The whole set current thing is what it does is it actually backs up the bank so that we can use this reset command later, and even this set command, which notice doesn't use set current. And this is so that we can have a kind of permanent bank change using set current, or a very temporary one using set, and then reset to undo the change. And this was used in Chibi Akumas, where set current would be used for the main bank that's in use by the code. But if you needed to quickly switch in something like the music for the interrupts, you would stop the interrupts, use set, play your music, use reset, resume your code, and everything would carry on as it was. And finally, we have our cartridge bank options here. So again, we're taking a value in the accumulator. This time it goes into C000 because that's where the cartridge bank goes to. We have to add 128 because we're telling it we want to set it to the high area. We can use any value from 0 to 7 to set the low area, but that would limit us to just 8 banks. So we're going to do the more flexible thing of having all 32 banks, because that's what we'd want if we were writing a game. That gives a full 512K. We set B to DF. We then out the bank number to DF. And then next what we need to do is actually page in the ROM. Now it's quite important at this point, the port we out to that does the ROM also does the screen mode. So we're having to have 2 versions here depending on if we're in mode 0, that's mode 0 there, or mode 1, that's there. And then this page is in the ROM accordingly. And that's how we can get access to our ROM. So how are we actually detecting the banks? Well, let's have a look. The principle's the same in all cases, but there are some differences depending on what we're actually detecting. So first we page in the basic 64K bank. We then write the value 69 to the bank base, which is a 4000, the start of the upgradable memory. We're using 69 just because it's a random value. Using 0 would be a bit too simplistic, or 255. You don't tend to see 69 very often in assembly code, so it becomes easy to notice when you see it in there. And then what we're going to do is we're going to page in bank D that was passed to us, and that's going to then switch into the 4000 range. We then read in the same memory location as we just wrote 69 to. We invert all the bits and we write it back. And then what we do is we page in bank 0 again, so we're back to our basic 64K. Now, if we don't have a 128K system, these commands here will have just overwritten the address that we wrote to here. So when we get back to this point, paging in the original 64K, we will find that it no longer equals 69 in hexadecimal, and so we go to our fail command here. So we're going to set the carry flag if we've got the memory upgrade, and we're going to clear it if we have not. So this is the one we use on the basic 64K systems, but as I said before, when we want to test for 256K on a 128K system, we have to do it a little bit differently. So what we're doing in that case is we're selecting the equivalent bank on our 128K system as the memory bank we were told to select on the 256K system. And we do that by zeroing out these 3 bits here. Because if you look here, those 3 bits are selecting the bank number, and we only have a bank 0 on a 128K system. Now I should probably point out at this time, a 192K system would be pretty rare, but I mean it's certainly possible. I've not gone up to 256 just for screen space limitations, but the code I'm looking at today does only test for 128K or 256, because in all honesty, the vast majority of people with any upgrade over 128 actually have 500 and 768. So back to our 128K bank test. So we're having to clear out the bank number here for our base bank that we're testing, but apart from that the code is exactly the same. And that's also true of the CPC Plus version. We're also writing our 69 to our base bank. We're then turning on the CPC Plus ASIC, which is at the same memory location as that base bank. We're then trying to change it, which will change some of the sprite memory, and then it will turn off the ASIC. Did that write change the basic memory? Well, if the answer is no, then we obviously have a CPC Plus. But if the answer is yes, then we do not have one. Now, of course, in all of these cases, we are writing a single byte to the 4000 range, and I'll be honest, the examples I'm showing you today don't ever change it back. So if that's going to be a problem for your code, if you've already got data in there at that point, you would want to load it in, back it up into the stack maybe, run this routine, and then pop it out the stack again and put it back. In Chibi Akumas, and I'm kind of intending in this would probably be the first thing you would do once your program loads, probably before you even start loading in the data. Because with Chibi Akumas, if you're on a CPC Plus, it's loading in CPC Plus sprites, and if you're not on a CPC Plus, it's loading in the regular sprites, and they actually exist in the same memory location. So it's not the case that you load all your data in and then work out what system you needed to use. You work out what system you're going to use and then you load the memory in. So I'm assuming it's not going to be a problem overwriting that 4000 address, but if it is, just please change it. So that's how we detect the banks, and then all that's left to discuss is our get hardware version command here. So this is going to be a little bit different depending on the system we look at, because it doesn't make sense to use our variables in the same way on all systems, because what makes sense for a CPC is it a plus or not? But on a Game Boy it will be, well, it's a colour system or not. And on an MSX it could be, well, has this got a V9K? So the variables will vary quite a bit because it's so hardware specific. But in the case of the CPC, we're going to use the D register, and that's going to contain 0 on a regular machine or 1 on a plus. The E register is going to be the memory, and this is going to be 0 for 64K, 1 for 128, or 2 for 256. And when we come to other systems later, we're going to mimic this quite a lot. So the D register will always be the hardware, and the E register will always be the memory. Okay, so that's the theory. And then all we do is we initialize our plus, we test our plus, and if we have a plus, we increase D. If we don't, and we do not, then we test to see if we've got 128K. If we haven't, then we return. But if we have, we then test to see if we've got 256K. And in both cases, we increment E if we find the test succeeded. That's really all there is to it. It's a very simple concept. It's just a pain to write it. So let's try it out. So here you can see D is currently 1 and E is 2. So that would imply our system is a CPC Plus with 256K of memory. Let's have a look. Well, you can see we do indeed have a CPC Plus, and we do have the 256K of extra memory here. So let's see that extra memory in action. So I'll just press the space key. So the 4000 address range is currently in the basic memory, and you can see it's got a 69, which is the result of our test, because as I said, I didn't change it back. We'll then switch in bank 1. Bank 1 is going to be C4. And you can see I've written C4 to the start of that memory range. And of course, we're banking switching between these. We're not actually writing them in between each of these screen displays. We're actually seeing the contents of the memory that were changed before these on-screen displays were executed. And then you can see there's C5. And again, that's another memory bank. And finally, if I just do debug and pause, you can see here we've got cartridge bank 5 paged in at the bottom of the addressable screen memory. So let's make some changes and we'll run the program again. So this time I'm going to go to General. I'm going to change to a CPC 6128 and I'm going to check the memory, and we're just going to have the basic 128K this time. And this time you can see D is 0 because it's detected there's no longer a plus system installed, and also E is now only 1 because before we had the 256K, now we only have the 128K. But because we're only paging in the basic 128K banks, our tests still work just fine. However, if I go to the debug and select pause, you can see now there's no cartridge bank selected anymore. So now let's do our final test. Let's change this to a CPC 464 Plus and run the test again. So this time D is 1 again because it's detected our plus features, but this time E is 0 because we have no extra memory. And if I press the space key, now you can see C5 is present in all the banks. Well, why is that? Because when we tried to do our bank switching up here, these commands had no effect. So what we actually ended up doing is writing this here, which is the C5, into our basic memory, which is our only memory. the 4000 range of the 64K of memory in the system. So that's why we have the same value here in all cases. We've got nothing extra to page in. So there we go. So that's how we can use the CPC Plus's features and the extra memory in a fairly straightforward manner. I hope you've enjoyed this lesson. We're going to be doing the same on all of our other systems. So if you've liked today's lesson, please like and subscribe, because we're going to be doing the exact same thing on all of the other systems we're covering in these tutorials. And as I've said before, while at the moment we're only covering the Z80 systems, in the future we're going to progress onto the 6502 and the 68000 series, which I'm already in a late stage of learning and creating these tutorials for, and they're going to be starting next year. Thanks for watching and goodbye.